like 2 projects. How are you?
Good. Ready to go home.
Making it.
Because we're actually having to like make the command tool.
You
Okay.
should complain now. You wouldn't know it.
Go home.
Try to concentrate on the material. Any questions on the theoretical lectures or administration? Yes.
So like the 3-page lab report, is it, do you have like a font or something? I can double space and stuff?
For the
You may
It just seems a little long.
APA standard, which is 1.5 space.
14 font, all the
try
periods.
1.5.
Sure.
You said 20-point font?
1.5 space.
Space.
APA standard is essentially 12 point times 11 point areas.
I was trying to see if I could go with like 200 points.
It doesn't matter which size you are using. The question is, are you using all of the information which is available there?
So
Right,
information is the important thing.
Information is what's important, not the font and not the size.
So
You're getting 1 page if you do that, then.
It's 1 page for
so
the
6 pages about my summary is not going to give me the bigger. Right.
We'll see. Any other questions?
So you said 1.5 space?
It doesn't matter.
Doesn't matter.
Put some
What space
information on
you're
there.
using doesn't matter what information you include. You need to summarize whatever you need to summarize. This is not important.
Yeah.
Much less important is the size of the computer. I mean, for my eyes, probably it's better to use 12 points. That's fine, I can zoom in. You like small fonts. So it's not a big deal if you're using any font you want. Any other questions? Okay, so today's topic is Bode diagrams or Bode plots. So Bode basically invented his own way of representing frequency domain in very simple way, very simplistic way, which was very important in previous years, 40s, 50s, when he developed that method for describing basically amplifiers or electrical circuits, electrical systems. He hadn't thought about signals and systems because signals and systems were not that popular at that time. So he published his book, I believe, in 40-something, 1940 or 45, I think. So it was a long time ago. And he developed basically very simplistic method to describe the system using 2 plots. One plot of gain, which is amplitude or magnitude, and another one is plot of phase. And phase describing basically the leg of the system for specific frequency. So we already know that any sinusoidal input will give you, for LTI system, sinusoidal output, which means that this output will be having different amplitude, obviously, or maybe the same amplitude, depends on the frequency, and it will have different phase, which means different delay. It could be forward delay or backward delay, so it will go that way or that way. So phase will be different. Now, just based on those 2 things, for each frequency you can identify those 2 numbers. What is the difference of phase between input and output? And what is the difference in magnitude, which is magnitude of the output divided by magnitude of the input. Those 2 numbers are exactly Bode diagram. Okay, so those are the numbers that we need to plot as a function of frequency. And those, for LTI systems, those numbers will be constant, which means for each frequency you will have only one pair of those numbers. So for each frequency you'll just put in, so you have some system, and this is how system identification works in frequency domain, for example. You put in some sine wave of amplitude 1 with some given frequency, let's say low frequency, close to DC, so it's very low frequency. Now, you have some system which you don't know what is inside of the black box. But you know that this system is approximated by linear system, linear time invariant system. If you put in something like that here you will get probably something like that. Some other sine wave, which could be shifted in time and different amplitude, right? So let's say this amplitude is 2. So we have gain of 2. right, for that specific frequency. So this is exactly the same frequency it has to be, because linear time invariant system is not changing frequency of the input signal. So if you have here frequency of 5 Hertz, this will be also 5 Hertz. But it may have different initial angle, right? So it could have different theta angle. So if this one is sine of whatever 2 pi ft, so f is your frequency that you put in some constant number, and t is time, here you will have a times sine of 2 pi ft plus some theta, minus some theta. This is what we know about any LTI system. Now, frequency will not change, amplitude will change, and theta will change. So to plot Bode diagrams, all you need to do is to put all of those as the functions of omega, or frequency, in that case. Also, generally, it's appropriate to use log of omega, which is just logarithmic scale, instead of linear scale. So basically, we'll go from 0.1 to 1, 10, 100, 1000, and so on. And the same thing here. Equal distances will have basically multiplicity of 10. So it will go 10 times each time when you go to the next distance of that kind. Okay? Now, so let's say you have frequency of 0.1.
Bless you.
So omega equals 0.1, what it means? Omega equals basically 2 pi f. So if omega equals 0.1, the frequency equals 0.1 divided by 2 pi. This is the transform that we are doing, right? So we know that this frequency in radians per second, and this frequency is basically in hertz, number of cycles per second. Now, for that specific frequency, let's say this frequency is here, you will get Z number and you will get Z number. So Z number you're plotting on the top graph, and Z number you're plotting on the bottom graph, you'll have only 1 point for that specific frequency, right? So in that case, A will be 2, whatever the value 2 here. And for the same value of frequency, you'll have another theta, which will be whatever the phase is, maybe somewhere here. Okay, so this is angle, and this is magnitude. Now, you're making the frequency faster. And here we get some frequency which is faster. Again, different phase, maybe different amplitude, maybe the same amplitude, who knows? Depends on the system, of course. Now, you put the next point, and next point here. Now, when you connect all of those points, you get Bode diagram. This is what it is. Now, having Bode diagram, you can identify back the transfer function. So if you do that kind of procedure to any system which is stable and accepting those sinusoidal waves, and you can measure the sinusoidal outputs, which are responses of the system, you can identify what that system is based on those two plots. And you do that using asymptotic Bode diagrams. Asymptotic Bode diagrams just meaning that you're approximating all of those curves as piecewise linear. So you're assuming that all of those poles will be those breaking points between linear segments. And this is how you know where your poles are and where your zeros are. Now, for example, stable poles, each time adding 20 dB to decay downwards, okay? Each unstable pole goes up. Now, zeros are also having their own properties in phase and in magnitude. So just based on that knowledge, you can identify what system is, what transfer function you have from the system. And this is why all of the topic is very useful. But it's also useful to solve all kind of simple problems like that. And I'm just repeating the problem from the previous lecture. If you remember, it took us like half an hour to solve that kind of question where you have some system. It was given by differential equation, but it's very fast to find transfer function from the differential equation just by looking at the coefficients. So we found the transfer function 2 over s plus 3. And the question was that if your input is sine of 3t, what will be the phase lag of the output compared to that phase of 0? Because you don't have any theta here, so just 0 angle. So what was the angle, do you remember? I believe it was minus 45 degrees or minus pi. Okay. Now, we did all kind of manipulations together. Okay, transport, back and forth, calculations, partial fraction expansion, and so on. Now, after we learn Bode diagrams, we don't need to do anything that complicated. Why? Because we know that the output will be also sinusoidal, and will be also 3t plus some sort of theta. Now, what will be the difference? The lag in the phase will be appropriate to that specific omega. So for that omega, you'll have specific lag and specific gain. We don't care about gain because we are asking about phase lag, right? So from here, omega equals 3 radian per second. This is our omega of input. And this is exactly the omega of the output, right? It's not changing. Now, what else we need to know? We just put in our S equals j omega, which is 3j, right? And finding the angle of that thing, because this is exactly magnitude of h and angle of h, of j omega. Which means that from this one, I'm getting to angle of h of j omega, and equals angle of 2 divided by j omega, and omega in that case is 3, so we can simplify right away. So it's 3j plus 3. This one is s. Now, what is that angle? So 1 divided by something, by some complex number. What is angle of that 1 divided by something? Is minus the angle of that something. Right? So angle of 1 divided by a is basically minus angle of a. When a is some complex number. So what we get from here is basically minus angle of 3j plus 3. Do you remember why is that true? You don't have to remember that. I mean, you can compute directly angle of z1 divided by z1. You can compute actual multiplication by conjugate and so on, but this is more practical to use z. This one is much faster. Why is that true? Because if you're thinking that this one is basically magnitude with angle 0, and this is some magnitude with angle. What angle is that? 3, 3. This one.
45.
So it's 45 degrees, right? So it's like amplitude 2 with angle 0 divided by amplitude whatever angle 45 degrees. Like how you use the polar coordinates, you take in that angle minus that angle. So it's minus angle 45 degrees, which is basically that one. This is what you get. So it's minus 45 degrees for 5/4 radian. That's it. This is the solution. And you obviously get just the same answer. So it's minus pi divided by 4. That's it. And you can use it for any angle, the same way. So you don't have to go through all of those complicated things. Any questions? Yes.
Will there be a situation on the test where you ask us to solve it the complicated way? Or will we?
I'm not that mean.
Okay. Cool.
Just a little.
And now he will.
Nah.
Thanks for giving him ideas.
Okay. let's try another question.
What
Yes.
happens when we have an S in the numerator? Whoever.
Same thing. You want that to be, let's say it was just 2s or 2s plus 5, whatever. So we make it j times 3 plus 5, and then we're computing angle of this one minus angle of this one. And get the same thing. You get difference in the same way. Okay? Clear? So just instead of s, you put in j omega everywhere in the entire rational function, whatever the rational function is, and you compute in the angle. This is exactly what that plot is, as a function of omega for any given omega. So you're basically taking just one point on Bode diagram, and this is that point in that case. Okay, let's try something tricky. This is closer to your test now. You have some Bode diagram of some unknown function. This is magnitude diagram. Let's say you have h in decibel, and it will look maybe something like that. Let's use some more. We'll go from here. And we'll go down here. Then we'll continue there. And the breaking points are, let's say, 1, 100, and this is log omega. So this is asymptotic Bode diagram. And it's given for the function h of s. I'm not giving you the function. You have basically not one function which is looking like that. You have, so it's not a single possible solution. But the question will be with single possible answer. Now, you're defining function g of s, and this function is defined like that. The question is how Bode diagram of GS will look like. Now, all we know is that this one is minus 20 dB decay. Okay, it's going up to 100. And then it's flat. So, how the Bode diagram will look like? What will change in Bode diagram?
For the phase or the amplitude?
This is amplitude, magnitude.
Magnitude.
We don't care about how phase will change, only how magnitude will change.
It will have another breaking point, minus 4.
It will have another breaking point where?
At omega equals 10.
Yes. So we need to add additional breaking point. This point will be here. So something will happen at that point. What will happen at that point? Will it go with bigger slope, smaller slope?
Well, more negative slope.
It will go with more negative slope because the pole is with plus 10. Okay, so it will add you some additional slope going down. How strongly it will go down?
Minus 20.
It's
Minus
already
40.
going minus 20, so it will go minus 40. Okay, so the slope will be twice as strong with minus 40 because you're adding one pole. Now, where it will start? Like what will be the first point which is still flat there? Like where it should move? Should it move from here somewhere?
No.
Not at all.
You say no.
The answer is yes, but the question is how. So pay attention that this one is in dB, which means this is 0 dB. What is gain of 0 dB? So what is the initial gain of that thing? What is h of 0 gain?
Do we need to put in the j omega?
Yes, so omega is 0. Like 0 flips to like DC gain.
So we
What is
over-
DC gain?
1 over 10.
1 over 10? No, I'm talking about h, which is given here by that plot.
0.
0 dB, but what is 0 dB? What gain is that? dB is log scale, right? So,
So we 20 log 0,
so log of what gives you 0?
1.
1. This is gain 1. And then log 10 of that thing is 0. Because Bode diagram is basically log 10 of h. This is what dB means. And 10 times. Okay, this is decibel, not 10, it's 20. Okay, this is how decibel is defined for given h. Now, so you know that the 20 log 10h is 0 for h at j is omega equals to 0, right? Now you have the same thing times that thing. So S is, again, j omega, right? And omega equals to 0. So what is the change that you need to do? Your initial gain was basically 1.
So we
So
should,
this thing was 0, so h equals to 1.
so we go to 1 decibel? Or,
So is there any change? How you compute that change? What do you need to compute? You need to compute that thing. 20 log 10 of absolute value of j times 0. This is what you want to compute. This is your initial point, right? That's where you start, at minus infinity. Okay, let's compute that. Let's put numbers in. So we have 20 log absolute value of h of 0, because this is what gs is, times 1 divided by j0 plus 10. This is where you start. Now, this one we know, right? So it's 1. This is a gain. Here. Because it's given by the green thing, 0 dB, it's 1 gain. Now, this is 1 over 10, right? So what is log 10 of 1 over 10? What is that?
Minus log 10 of 10,
It's
so minus 1.
minus
1.
1.
It's negative 20.
Negative 20 dB. Okay. So essentially we need to start from minus 20. So let's say from here, it's minus 20 dB. And then it gets here, goes in parallel here, up to that point.
So steeper
So
slope.
exactly in parallel. In my case, that's let's say from here. So it should go in parallel from here. It goes like that. And from now on, it should go stronger here. So it was minus 20 here, so here it's minus 40. Until it gets to here. Now what?
theoretically it would go to minus 20 slope now because you had to have plus 20 slope
Yes.
at 100. So,
So now you return back like that. It should be kind of parallel to that slope. That way. Better drawing. So it's minus 40, and then back to that slope, and continuing forever that way, going down.
So it never will go down.
Nope.
Always will go down. Now, pay attention. Is it really getting to anything like negative gain?
Not changing.
No, it is changing. It's going always down. It's
going
getting
your
lower
way.
and lower and lower gain, lower and lower. Now, is it ever getting really negative gain, or maybe it's always negative gain? So in dB it's negative, but in real gain, without dB, actual absolute value of h,
It would approach 0.
it will approach 0. So it will never be negative. Magnitude is always positive or 0. You cannot have negative magnitude. There is nothing like that. Magnitude by definition is absolute value, so absolute value cannot be negative. So this thing will just, essentially, the line which is going always to minus infinity in dB, essentially means that your plot will go
To 0.
gradually to 0. Okay, this is what it means. Exponential. It will look like that. Okay, this is kind of questions that you might get on the test, where you need to understand some concepts, how it works. Any questions on that? Okay, let's try something else. We want to plot some Bode diagrams of a few simple functions. And then we will move to some more complicated example with more sophisticated Bode diagrams and asymptotic Bode diagrams. But let's start with simple Bode diagrams, which are realistic Bode diagrams. You want to plot Bode diagram of some simple function like g of s equals something like that, for example. Now, to plot Bode diagram of any transfer function of that kind, so this is transfer function of some given system. To plot transfer function of any kind, you're replacing s with j omega. And then you want to plot everything as a function of j omega. So Bode diagram is nothing else but 20 log 10 g of j omega and angle of g of j omega as a function of omega. So you want to plot basically those two plots as a function of omega. That's it. Now, we'll start plotting that without using any logarithmic scales. We will try first linear scales and see why it's much more efficient to use logarithmic scales and not linear scales, because the graph will look pretty horrible when you're using regular linear scale. So let's see what we get from here. Let's start with magnitude. So g of j omega equals 1 over j omega plus 2. From here, absolute value of g at j omega equals 1 divided by square root of omega squared plus 4. Right? So this is just Pythagoras theorem. You have j omega here and 2 here. It's your complex number. You're looking for magnitude, which is the length of that vector. So it's 2 squared plus omega squared equals that thing squared, Pythagoras here. Okay. Any questions on that? Okay, so this is just absolute value of that vector. Now, basically we need to plot something like that. And how it should look like. So this is magnitude, which is absolute value of g, as a function of omega, linear graph. Where it starts?
Zero.
No.
100. Yeah, 100.
So this is 0.
One.
Omega equals to 0. So what
One
happens when
omega.
omega equals to 0?
You get 100.
1/2. It should start somewhere 0.5. Now, we will go, when omega is super high, where it will go? Somewhere
Zero.
here. So it should end up somewhere here, going almost to 0. Now, is it coming up ever from that 0.5? Is it coming up or down when omega is increasing? So since omega is increasing, that entire thing is increasing, right?
Right.
And 1 divided by that increasing thing should always go down. So it probably will look something like that. Something of that kind. Function which is going down and approaching 0 forever. It never gets to 0, right? So you never can get really 0 here, but it's approaching 0 after you get to some big values of omega. Now, let's take the second part, which is phase. So you want to compute angle, and then it will be angle of 1g omega plus 2, which is minus angle 2 plus j omega, which is something like that. I don't know if you are used to notation of arctangent or tang in -1, the same thing. Inverse tangent. Okay? So it's just taking this one divided by this one and arctangent. Exactly the same way. I mean, you finding that angle. And that angle, omega divided by 2, is basically tangent of that angle, right? So you need inverse of the function to get the actual angle. Now, how this thing looks like? Again, this is omega, this is angle of j omega. So let's see where it starts when omega equals to 0. Just to remind you how that function looks like. Looks like that. It starts at minus pi half to pi half. Something like that. So what happens for omega equals to 0?
0.
It will be 0, so it will start at 0. Now, omega will grow from that point of view. What will happen to that function? Will it go up or down? Since you have negative sign here, it will go down. So it will be that thing flipped upside down, so it will look over going down from here. Now, where it will be when omega is huge?
To its limit, negative.
It's limited. So you have some limit which is negative pi over 2, and then it will approach that limit somehow. Something like that. This is how phase will look like in linear axis. Okay, can you get much information from that? Well, not really. It's too, the curvature is too high. to get any useful information from that. And this is why it's much better to use other approach, where you have log of omega and decibels for the amplitude, for the magnitude. Now, let's compute those. So now we're trying to plot actual Bode diagram, which is logarithmic scale. So, 20 log 10 of that thing, and that thing you can write as omega squared plus 4 minus 1/2. Right, because this is something divided by square root. Okay, so minus 1/2 will multiply 20 by the rules of logs. Remember those rules? So it will be minus 10 here. It will be minus 10 log 10 of omega squared plus 4. Okay? So this is how it will look like. Now, how it will look like in Bode diagram. We need to make it higher. Let's start with something negative. Where it will start. So omega equals
0.
some small, no, you never get really to 0, but we can approximate it with 0. Because this one is not starting at 0 now. If you remember, logarithmic scale
So it's 1.
starts at some point. Okay, just start it randomly somewhere, small enough, compared to the sizes that you have here. And then this might be 0.1 or 0.01 or whatever, but you never get to 0 because actual 0 at minus infinity. So you need to go to minus infinity to get to actual 0 of omega. So you never get 0 omega. But what happens here for 0 omega? You get log 10 of 4 times minus 10, so it will be some number, right? What will be that number? Do you have a calculator?
Let's do that.
Okay.
Negative 6.02.
So negative 0.6, 6 point what?
02.
Approximately negative 0.6 dB. So it will start from here. Now, interestingly, almost nothing will happen to that thing until it will get potential pole. But, so it will be almost flat. So where do you have the pole? So let's put some scale here. Okay. So let's say you have 0.1, then you have 1, 10, 100. Now the pole is at 2, minus 2, negative 2, right? So logarithmic scale, it goes like that. First step is biggest one, then smaller, 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 and so on. Remember how logarithmic scale looks like? Logarithmic paper. So it's approximately here. This is your location of the pole. So asymptotically, it will look almost like that. Flat until that thing goes here. And then it will go down minus 20 dB to decay. Okay? So this is how it will look like. Now, real one will be a little bit different. So it's not exactly flat here. It's going a little bit down. So it looks like that. So this is real one. When you plot that in MATLAB, you're using Bode function, you get some plot of that kind. That distance, interestingly, is always 3 dB. Have you heard about 3 dB distance in amplifiers and other circuit courses? That bandwidth is defined by 3 dB point. No? So basically, this point is very popular in design of amplifiers and in many circuits, where you need to define some bandwidth of your circuit. Are you familiar with bandwidth? The width of your band, passing band of some kind, or you're designing amplifier, or designing filter, or designing any other circuitry which has some characteristics in frequency domain. You're always defining how wide is your band, that you can pass frequencies in that band, and then you're not passing any other frequencies. So those frequencies defined by that point, by the point where your poles are, okay? And your poles will identify how wide is your band, like which frequencies you are passing with your system and which frequencies you are blocking with your system. You will learn more about that in the next lecture on filters, but generally speaking, this point for each pole, it will be minus 3 dB point. So realistic function compared to asymptotic function will be 3 dB per pole lower. So you'll have kind of curvature, and this point where you have the pole, it will be 3 dB lower. Is that clear? But you plotting that in MATLAB, it will give you that automatically, so you can check that you have that point. So theoretically, it's interesting that it's always the same number. So this is how it will look. It will look like Z in asymptotic domain. Asymptotic Bode diagram is black, and realistic one is blue, real one. Okay, for that kind of transfer function. Any questions? Okay, so now we need to do some basic derivation, which is useful for Bode in general. I published one page with all kind of Bode asymptotic functions. You need to be familiar with that page, and I recommend to use it. Have you seen that page in Canvas? With all of those functions for one pole, for double pole, for zero, and so on for constant. Now, all of those functions, if you pay attention to what you have in those tables, all of those functions are not given in that shape. They're given in the shape, let's say 1 divided by 1 plus something. It's not like 1 divided by s plus something, because generally we used to see functions of that kind, maybe like 5 divided by s plus 10, right? Or s plus 10, or s plus 1, whatever. In that kind of shape, right? All of those functions are given in completely different shape. And there is reason for that. It's not given in the shape like something divided by s plus 10. It's given in the form of something like that. It's given some constant, maybe divided by 1 plus j omega divided by 5. Something of that kind. Okay? Or 1 plus j omega divided by something. So you always have only that form. Why do you think it's useful for Bode diagrams? Why all of your plots are of that kind and not of that kind? Not of that kind. Not like that. So you're having, instead of that thing, you need to write something like that. And here you'll have 1. Okay, so dividing by 2, and here you have divided by 2. Which is obviously the same, but this is how I want the function to be represented to plot Bode diagram. Why is that? Any ideas? Why would that be useful for anything? Like check for omega 0. So what happens with those things where omega equals to 0? In that representation.
It's just a constant. J.
It will be just whatever is written here. If k equals to 1, the gain will be 1. Right? Amplitude, magnitude will be 1 for those. For those not. For those it will be a ratio of whatever you have on the top with that number. right? So when you're adding Bode diagrams, you're adding them pole by pole, 0 by 0. So basically, each time you're adding some additional plot of 0 or adding additional plot of pole. And we will see some example in a second, but the procedure is just to add them gradually one by one to get final Bode diagram, pole by pole. Now, if each one of those will have completely different gains, this basically means that they all not starting from 0 dB, because gain is not 1, obviously. If they don't start from 0 dB, you will have shift to shift them up or down each time you add a component of that kind. Exactly like we did here. You see? So each time you add a component of that kind, right, which I deleted because that's plus 10. Right? Each time you add a component of that kind, you need to shift the initial baseline, which is not convenient. It's much easier to pull out all of the coefficients of the gain, to leave them aside, then to plot all of that thing with gains 1, and then to shift the entire plot by the gain. It's much more convenient. Instead of each time that you add in a single pole, you need to shift the entire thing. Okay, and then you need to redo all of the plot. That way you can just start from left to right to get consequently to all of the poles and zeros, and then to start going up or down depends on either pole or zero and so on. Okay, this is the overall idea. Now, is it always possible to get to that representation, which is something divided by 1 plus j omega divided by something, or 1 plus j omega divided by something? Is it always possible to get them from any transfer function like z, for example? Is it always possible to write it that way?
Yes.
And why? Why it's possible? What is the technique to write it?
Divided by.
Let's see some simple example. Okay. Let's say we have s plus 5 times s plus 6, 3. I'm just throwing some random numbers, it doesn't matter. Okay, so now I'm replacing every s with j omega, right? Because this is what we do to find Bode diagram.